All right, you guys have any questions? Again, just let me know. Speak up or put them on the chat, okay? So in the last class, we were talking about the density of states and why that's important. And let me just do a quick recap. So the states of the system were evenly, in that case, for the free fermion gas, were evenly distributed in K-space. And what we said is that when we have a very large number of states, which is the case even for things that are about a micron size, counting them is not efficient when we have to do summations. And what we can do then is, instead of counting with this approach, right, we actually go and do a summation. Now I'm going to use length square as my volume, right? Because if not, somebody gets mad. His name starts with a C. And then this is in 3 dimensions. So I have the right there. And then we had that this is the integrals for this function that at this point I haven't defined. So this is an important equation. I'm going to label it 1. And this sum in equation 1 is over all of the k vector states allowed for the free electron gas. So for every wave vector, we have 2 electrons. This is due to the Pauli exclusion principle. So we have the up and down electrons. And then the most important function that we're going to use is the density of electronic states. So there's a whole set of density of states functions. So the one that I want to talk about right now is called the density of electronic states. And what we have is that this one is given by this D function that depends on K, and is given by the 2 for the spin up and spin down, the degeneracy of the system. And then this 2 pi cube, the cube is for the dimensionality. And what I left with telling you last time was that this was towards the end of the class. And you can see this mouse thing on it, right?
Yes.
All right, so this D of K actually doesn't depend on K for anything. But in this case, right? And it was just kind of like the separation of the energy levels that we had. All right, so this is the thing that we have for the free electron gas. And then it could be, this is just the separation of the levels. And this one comes out and is defined from the following quantity, which is the summation over all of the K states level by K that have a spin of this big function f of K is going to be equals to the volume and then the integral over the dk levels of the dk states of this function d of k that we're coming up with, and this function that holds the information that we want. And at least in this case, this d of k does not depend on k. All right, so any questions up to here? I think that this was covered in the previous class, but I want to make sure that we are starting all in the same spot.
I had a little question. I guess I'm a little. So the factor of 2 we have in the definition of dk, we have that 2 because of the spin, right? I think you mentioned that in last class. Yeah. So I was thinking that since we already have that factor of 2 in dk, doesn't that kind of takes care of the spin factor? But then we are again in the summation, we are again summing over the spin. So
Right. So let me go back over here, right? The way that we obtain this function is from this. So that's why once we do this summation, that's where we get this 2. Does that make sense? So that's how it's defined. The 2 comes from doing this part of the summation.
But I mean the decay we have in the second equation, it already has that 2.
No. The first equation is decay,
Mm-hmm.
and we obtain it from the third equation.
Oh, okay.
So that's
Dr. Borunda.
Yeah.
I remember last class you said that 2 comes because of the fact that we have spin up and spin down. That's why we put 2, isn't it?
Yeah, exactly. So this is the way that we define that equation. So this third equation has the spin right there, and the spin is up and down. And in systems that are not ferromagnetic, normal systems have that. It's just the same thing for spin up or spin down.
Mm-hmm.
Now that 2 is coming because of that definition. So this is my definition. It's not that the 2 is in both places. Okay?
Okay.
All right. So then, yeah. So then we have that this d of k. So we can use a shorthand. And this is just so that we have a functional that depends on dk. And basically we just define it as 2 over the volume. And that summation over k. Again, the 2 there is for spin. And that is equal to this integral. You see, again, I'm just using shorthand so that I can do this definitions. And I have this definition right here. So that is something that I can then do calculations with. And but basically what this tells me is that I would have this dk, substituting it in, I would just get that 2 over 2 pi cube integral over dk. So that's I think where I stop, because I didn't want to get into the next portion. So I'm gonna get into the new stuff now. But the most important thing is to remember this first equation right there, okay? Questions?
We can't really see when you said this equation. We can't see that pointer.
Let me put numbers on them.
Okay.
This one and this one are both important, 1 and 2. Okay, so I'll just refer you back to those 2. So I'm gonna erase the screen and then go into the next new stuff now. So unless you have questions about it. All right, let's continue then. So now I'm gonna be giving you the most important of this density of states. And the most important one is the energy density of states. The energy density of states. There are several of these D functions. So the density of states could be for different things. They're all called density of states. And the only thing that makes them different from each other, basically everything is a density of states, except that, and they're all giving you different things, but they're all called density of states. And the main difference is what is the argument of the density of states. So the most important of them is the energy density of states. And that means that for this energy density of states, what I would do is that I have this definition again of my function. And now the argument that goes here is energy. And this energy, we're gonna do the free electron gas. So basically the definition is that we will have volume, and then our integral is gonna be over the energy. This d of E is the density of states, and then we have this guy. All right, so just as a reminder, for free electron gas, we're using that this is my function of K of the energy, and this is how it works. So now let us find this density states that its argument is the energy. So what we would do is that we would do this equation again. So I'm working it out completely because, and I haven't written the homework set yet, but you're gonna redo this for other parameters, okay? For other, you're gonna play with this thing. So I'm gonna give you the whole, how to do it from start to finish. And so you can do it for other kind of systems. So I haven't written the homework. I hope to have it for you by the end of the week. In this case, we're doing volume times this functional times this little monster right here, right? Now, I need to play with, so I'm doing some math. So the math trick here is that I'm gonna be kind of like multiplying by 1, introducing another function that is basically just 1. So what I do then is that I have the same thing, and then I'm gonna do, this integral is new, right? But I'm basically going to be multiplying by 1 because I'm putting that integral and then I'm adding a delta function for it. Okay, so if you look at it, these two things right here, this part and this part together are equal to 1. Questions about that? Right, so then that means that with that as my definition, then I can say what my density of states function is. And my density of states is just this integral times the delta function. Questions?
I'm so sorry for the delta. Is it I or is it E or EK?
Sorry?
So at EK, that integral will go to 1, isn't it?
Right, so look at it this way. I'm sticking spotlight, there we go. So this function is for EK. This delta function is gonna say for all energy, so this integration is over all energies, but then this delta function is gonna be such that the only one that I care about, the only one that this is gonna matter to is when energy is equal to EK. But then my energy is here. So this is an energy now. Sorry, my hand.
So this FEK equal to I, that's what you're saying.
I'm sorry?
So at the end, FEK is equal to this I. I also, is it identity matrix or is it 1?
FE right there. That is supposed to be an FE. So I went from being.
Dr. Barunda, he's asking if what you have written in blue down there is equal to I, it's equal to 1. I think that's where his confusion's coming from.
Yeah, exactly. This times this is like multiplying by 1, right?
Yes. So now this is EK. And since you have this FE, that would be FEK2. So this FEK is equal to 1, or is it equal to I?
I'm
Identity matrix.
F of E of K to F of E. This delta function is taking me from F of E of K to F of E. I'm just doing by sticking the delta function in there, I get to get rid of this K because this E right here is going to be shifted to EK when I do this integral times the delta function on this function.
It's just the integral property of Dirac delta function.
Right.
If you just look at that identity, everything would make sense. I promise you. So just the integral property of Dirac delta function.
Right.
That's basically what's happening.
Kind of like multiplying by 1, right?
Yeah, exactly.
Not changing, just expanding by sticking something new there.
Yeah, it just changes the epsilon to epsilon k, and the rest of the thing goes 1.
All right, so now let's go back to the free electron gas. Let me clear this up. And talk about the free electron gas again. So then I have that let me start with the definition that we just figured out what it was. My energy density of states is just this integral times the delta function, like that. And I can rewrite this as, because I already have my definition for that delta K, right? 2 pi cube and then my delta function. So at this point, if you remember, energy depends not on the K vector, but on the magnitude of K, right? So this integral right here is over the K vector, but I actually don't need to do it over the K vector. In this case, there's no K direction dependence. It's just K magnitude. So what I'm gonna do is go to polar coordinates. So that means that I can go to polar coordinates and writing this out, it means that I go from 0 to 2 pi d phi, and then 0 to pi d theta sine theta. And then this one goes from 0 to infinity, k squared, and the delta function. All right, so now we can do the math right here. And we're gonna end up with 4 pi times 2 divided by 2 pi cube. And at this point, I want to express K in terms of the energy. So this is what I'm gonna do. I know that this guy, right, is actually h bar squared, k squared over 2m. So what that means is that k squared is equal to what? 2m energy, whatever the quantity energy is, divided by h bar squared. And then the other thing I wanna do is that I wanna go not in dk, but to dE. How do I do that part? Anybody?
The dispersion relation?
So what is the transformation that takes me from dE, from dk to dE? What would I have to do? What could I do? What math equation would I do?
Isn't it simply the change of variable, like the thing we do in integration all the time? I think it's just that.
Right. So then what I need to do then is just a change of variable. And I go, again, this one goes from 0 to infinity, because if you go from 0 to infinity in k, you're also going from 0 to infinity in k, right? And then I'm gonna do this one. And then on the bottom is the absolute value of. So with that, then I have the k squared. And then I have the delta function. And I guess in this delta function, since I'm putting the little vector right here on the little vector on the case, I guess my wave vector has to have this. But again, it's not depending on that, right? Questions? All right, so then this is an integral that you can do.
If you don't mind, I'm so sorry. Your D and DEK, are they the same?
Let's see, what D
So
and
the variable you chose, E, and then you did the integration based of EK, are they the same?
all right, no. But this delta function makes them the same.
Okay.
That's why you use the delta function, because you bring this delta function to grab this guy and convert it to E. And basically doing the integral with the delta function just lets you solve it in 2 seconds, right? Because you just have to figure out what this guy is, which you can do. You just take the derivative, you figure out what this guy is, right? Because you know what is the relationship between E and K. Then you can figure out what this guy is. Then this integral that goes from 0 to infinity over the energy, dE, is just whatever the function is here, is taking the value of the energy, and you're done. And once you do that, you get the solution, which in this case is D of E is equal to mass over h bar 2 pi squared and the square root of 2m times energy. So that's the equation for the density of states of the energy. At this point, you can compare this to this exactly with equation equation 2.24 in the book. And if you look at the book, there's actually a typo. According to this development, there's a typo because he's missing a factor of 1/2. But it's the same equation. It's just that there's a few typos in the book. All right. So comparing to that, you see that there's still the same equation as there, except for that factor of 2 that is missing, but everything else is the same. Questions? All right. So then let's look at how to use the same idea and now to do a calculation for the number of electrons, which is also done in the book. So the book sketches this, and this is maybe a little bit simpler calculation, but you can do it too. If you change, for instance, if we were to change now, if you were to change this thing, that it doesn't behave as the proportional to the square of the K vector, you can also do it if you change that to a linear relationship, right? Like let's say the energy now depends on K, not on K squared. Then everything is the same. You would just have to change the math here to square it or whatever it is that you need to do. Let's say that your density, that your wave vector, that your system is not 3-dimensional, you would just have to change this thing to 2-dimensional or to 1-dimensional, and you can still do that same calculation. All right, so now let's talk about the next type of calculation, which is the number of electrons. So this is not difficult. It's actually pretty easy. What we want to know then is count how many electrons fit in a sphere of radius of kf. So what that is just this summation, where we have labels of the states over the k wave vector. And we also know that we have to take a spin into account. And the next thing that we have is that there's a function f of k that tells us that is 1 if the state is occupied and it's 0 if the state is unoccupied. So we use equation 1, and we can rewrite one. With equation 1, we could rewrite this, and this n is just volume times this functional rate times a function f of k. So this f of k for our electrons at 0 temperature is the Heaviside state function. Are you guys familiar with the Heaviside state function? Yes, no?
I remember it came up in E&M quite a bit.
Yeah, okay. So you have it then. And then this monster is a 0 or a 1. When is it 0, Nate? You remember?
Sorry, can you repeat your question? Are you asking when it's 0?
This Heaviside function.
Kind of like the delta function, the same parameters. When kf is equal to k, it goes to 1, and when it's not, it's 0.
No, actually, that's a delta function, right?
Yeah, I was assuming this was like the delta function.
This one is actually 1. And then at this point goes to 0.
Okay, so it's 1 everywhere except,
Below
it's
KF,
1 up into kf and then 0 everywhere else.
exactly. Below KF is 1, above KF is 0.
Okay.
So that's your Heaviside function. And yeah, you saw it on E&M a bunch of times. So if you do this integral, what you're actually getting is, and by counting this, you're just getting the volume of a sphere. And then you use equation 2, the one that I had labeled to before, do the integral. And then you get that you would get volume 4 pi cube, then 4 pi over 3. The 4 pi is coming out from the 0 to 2 pi d phi integral and the 0 to pi sine theta d theta integral. And then this goes as kf cube. So it's not the same as the delta function. It's just giving you the same, it's the same idea though, that you're gonna use the volume of a sphere and calculate this. So here you get the values for this, and you can compare this to equation 2.21 in book. And this one doesn't have a typo in the book, but it's the same idea. So what we're talking here is how many electrons are in your system, and you're just counting all the way to the Fermi surface. You can also talk about little n, which is the density. So number of electrons divided by volume. And that means that this is the density of electrons. How many electrons are on your system? And what you see here is that this density is related to Kf. Because big N is related to Kf, little n is also related to Kf. So you can write that the wave vector, the Fermi wave vector is 3 pi squared little n and cubic root of that. And you can put numbers in there, and you actually get that is 3.09. Then whatever the density of your system is, times the Armstrongs per unit, cubic root of that, and you get that that comes out in inverse Armstrongs. So that can give you an idea of what a KF is. So the density of electrons, this little n is the density of electrons. And sometimes people talk not about the density of electrons like that, but actually bring up what is the size of a sphere of a free electron gas that would have the same density of electrons. So sometimes we talk about a density of electrons that is related to this radius of a sphere. So there's a sphere, and the volume of that sphere is going to be given by 4 pi divided by 3 r squared is equal to this volume over big N. And that means that we can rewrite this for Rs as just being 3 over 4 pi and then volume over big N. All of this. So those are some of the parameters that you might see in the literature when they're talking about how many electrons are on the system, which is basically equivalent to how big of a radius a sphere would have if it was a free electron gas of that system. Questions?
If you don't mind. Oh, there was someone else, sorry.
So go ahead, whoever wants to
Oh,
go.
it's me?
Yeah.
Okay. Since you said it will come to the homework again, so I just wanted to make sure. With the previous integral that you've been describing, this is the Dirac delta. When you say E minus EK, what you mean is that EK is positioned at the positive x-axis. So this will be valid if the value is EK. So that function should come out as FEK, not FE, I assume. So yeah, just to make sure, since you said it will come to the homework again.
So basically it's just so that you can do the integral without doing the integral, right? Because the delta, that delta is just when you do, let me do.
My point is, can we exchange those two variables without any problem? That's what you did there.
That's what I meant, that you can do the integral without even thinking. Because all right.
Well, I know how to solve that integral. It's just the variable that you chose is confusing me. Because I know that the specific location that the integral will be equal to the function. Function will be valid at the point of that Dirac delta, which would be FEK, not FE.
It's probably the same thing. We're just talking about, maybe I said it confusingly, but you're right.
Maybe there's a difference in meaning, like E and EK. EK is a combinations, right, of the density density functions, but E is one of those, isn't it? I thought. That's why you use EKs and E's.
Yeah, well, if you're confused when doing the homework, just let me know and we can go over it. But
Okay,
I think that you have it. It's just an easy way to do the integral that way.
Maybe, yeah, I thought it would be helpful for the others too, but thank you. Yeah, sorry.
All right. Any other questions? I don't know if anybody else had a question. I don't see any.
Could you explain again when we found the KF and you put 3.09 the Angstrom units?
Yeah, so the unit here. So what I'm saying is that this is the density. Density is going to have a unit of 1 over volume, right? So therefore I have to multiply by this length. And when I get it by this length, then I have the right units here. Whatever value of my density is given to you in the unit of density, right? So it's how many electrons or how many particles over a volume. So once you do that, how many particles over a volume, then you still have to multiply by this guy and then take the cubic root of that value. And then your unit still has to have at the end this value on the end.
So, because if I multiply units over volume.
Oh, sorry. Yeah, I see what you're saying. There's a cube right here that I'm missing.
Okay, thank you.
Right there, right? Sorry, my bad. Yeah, this is a cube. Exactly. That's the unit that you need for it to match up. All right, so let me go to the next thing then that I wanted to talk about. So now I'm gonna talk about what is the meaning of KF, density, Fermi level, and then our new friend, the density of states. So the energy of the most energetic occupied state is called the Fermi energy. So this is the energy of the most energetic occupied state. And what this is Fermi energy like this. For the free electron gas, we said that it was related to KF this way. And then if we look for units, it could be something like this, 36 times 0.46 times the density. Then here, let me not forget this A cube. This is to the 2/3, and this would give you, with that numeric value, will give you the Fermi level, the Fermi energy in terms of electron volts. Then we have another thing that is called the Fermi surface. This Fermi surface is the collection of Ks such that the electrons with wave number K have energy EF, Fermi energy. So this is what the Fermi surface is. Another thing that we can talk about is the Fermi velocity. So I think we touched upon a little bit about this already. So the Fermi velocity is just defined as Fermi velocity and is given to you as this quantity. So you see h bar kf, that's kind of like a momentum divided by mass. And this one comes in units of 3 to the 58, some density in Bohr's. Then you have to take the cube root of that times 10 to the 8 centimeters per second. Okay? So now, some values of n. So n for some elements so the simplest one is lithium. Lithium has 4.6 as value of n. And actually this n would be in 10 to the 22. This is the units that are used in papers. 10 to the 22 over centimeter cube. Another one that is in that same row is sodium, and you get 2.54. Another one that is related to that is potassium, and you get 1.3. Rubidium, you get 1.08. And then cesium, you get 0.85. So I don't know if you guys know, this is the first row of elements, right? And as you go from lithium to cesium, what is the difference between them? Babu?
Yeah.
What
Yeah.
is the difference between them as you go from lithium to cesium?
So that number of electrons that going to be decreased, right?
Yeah, the number of electrons.
Density, electron density.
Also, which atom would be bigger, you think, lithium or cesium?
In terms of density,
In terms of
cesium.
right, exactly. So what you see is that there's more lithiums packed in one area, in one volume, than cesiums. But all of those guys, because they're from the first column in the periodic table, they're just giving you one electron, right? So that's how that goes down.
Yeah.
Another one that is interesting to look at is copper. Copper actually gives you 8.49. So you can see that copper has way more electrons in density than the other materials. Okay?
Yeah.
Those are some of the values that you would find and for this particular ones.
So can we relate this to how good conductor will be this material? Or
there's a trend for that, but conductivity doesn't just mean on the electron number of electrons conducting. You also have things about how nice the lattice is, the crystal lattice, because electrons would matter and not move as fast as they should. But you can see how fast they're moving based on this density right here.
so, for example, gold may have a similar electron density as copper, but it's better conductor because of their reasons.
Yeah, it has in the same range as copper. I believe it's around 5 or 5 point something, and it's just more denser than copper, right? Because copper is way lighter than, so it would go copper, silver, and gold. All right, so then the last, yeah, go ahead.
Yeah, so this number of density refer to the valence atoms, electrons, not to the total number of electrons.
Right, just the electrons that are in that density that you would find on that volume.
Okay, thank you.
Yeah. What is the significance of the density of states? So this is something that we have spent so much time talking about, right? But at this point, if I ask you, why is it important to have it? What would your answer be, right? What is the significance of it? So this density of state, what it's telling you, actually the density of state, the only one that is important and the only part that we care about is not the whole density of state, but actually we just care about the density of state at the Fermi level. But this density of state at the surface, at the Fermi surface, is really important because almost all of the electronic transport properties depend on the shape of this density of state. What is the density at the Fermi surface? All of those properties depend on the density of states. So let me give you an example of this. Let's see. I'm gonna draw here. So this is Kx and Ky. There's Kc coming at you if you wanted to, or this could be two-dimensional. And then I'm gonna have, there's a circle here. Let's assume that this was symmetric, right? And that I know how to draw. And then all of my energy, all of the, here inside of it, there's a bunch of energy states all the way across like this. So this is all filled with, basically with K states, right? So the most important thing now is to look at this. This thing right here is the Fermi surface for our pre-Fermi gas. It was a perfect sphere. And what we have here is a Fermi sphere.
Can I ask a question really quick, Dr. Baranda?
Yeah, go ahead.
So when you said this is a perfect sphere for a free Fermi gas, does that indicate that for other physical situations that this isn't a sphere, that it takes on a different shape?
Yeah, and I'll show you pictures of it right now.
Awesome, thanks.
All right. So then let's say that you had an electric field. The electric field is applied to the system, right? So you have an electric field, and this electric field is going to be applied in that direction. So what's going to happen then is that, let me redraw it carefully. I can do this. So this is the original one. And then when you apply the electric field in that direction, you actually are gonna be like this. So the electrons in an electric field, because of their negative charge, get pushed in the opposite direction, right? So there's an electric field pushing on them. The electric field is in that direction. So that means that the electrons get pushed in that direction, right? And now you have an imbalance because the electrons that are here. So let's look at it this way. In the original one, there's an electron here that is moving with that speed in that direction. But there's also an electron here that is moving with that speed in that direction. So they cancel out and there's no net current flowing, right? At this point, there's an electron here because of the electric field that cancels an electron here. But then this area right here doesn't get canceled. Those are the ones that are giving you electrical transport, electrons moving that don't get canceled by electrons moving in the opposite direction. And it's just these guys right here. Does that make sense? Questions? So that's because you applied an electric field. Absorption of heat happens the same way, only the electrons on the Fermi surface respond and absorb heat and start vibrating more. And the reason for that is that if you have an electron that is down here and it wants to absorb heat, that would mean that it absorbs heat and it has to go to a different state because it has more energy. But once you get around it, he says like, okay, I want to grab this energy, but to grab that energy, I have to find a state nearby that is unoccupied. And to grab that energy, it says like, can I move into this other higher energy states? And there's no available one. All around here is full all around here is full, all around here is full, except for these guys over here that when they see that, oh, I want to grab some heat, they just go over here, right? And only the ones on the surface can absorb heat and get more energetic. So that's why only the electrons and the density of states of the electrons at the Fermi surface would matter for electrical transport, for absorption of heat, for responding to applied fields. All the electrons with energy below the Fermi level do not contribute to the transport because all of the states around them are occupied. And if you have a perturbation, in order to respond to that perturbation, they would need to be able to move to a nearby state. So the last picture I want to draw here is very similar picture, but what happens when you have light coming in? So again, this is the KY, KX axis. I'm gonna have my Fermi sphere occupied, right? So it's gonna be here. There's my Fermi sphere, all of those states are occupied. And so what happens if you have some photon coming in? So now there's gonna be light coming in. This light comes in, and what is gonna happen then is that I'm gonna excite, when the light gets absorbed, I'm gonna excite an electron from here. So there's my electron, and you guys can see the little dot right there, right? And it gets excited, and it gets put outside of there. So now there's an empty space that was left behind. We call that one a hole. Electron that absorbs the light, the photon, leaves the Fermi surface and goes on top of the Fermi surface to some state up here. And then that electron is here by itself in an empty state that was previously empty. And now there's a little hole right here. That was because it absorbed this light. Questions? Nope.
So can I ask regarding the electric field example?
Yeah.
So would the sphere just slide of exactly one position just to move the electrons that are on the surface, or more than one position?
It depends on the magnitude of the electric field. So it would displace itself by how much the electric field you're applying is. So you would need a little bit of a threshold to move it forward by one eigenstate, right? But there's so many eigenstates nearby that is going to move it with a very tiny electric field even. But yeah, you need to have enough electric field to move it, and the distance that it gets moved here depends on the magnitude of this electric field.
Okay, thank you.
All right. So then this is how XPS works, how the electrons at the bottom get promoted to the top in this picture where we're talking about Kx and Ky being the axis there. Any questions? All right. So now let me see, how do I share? I'm gonna share now. Share. Come on. All right, let's go back to Zoom. Stop sharing. All right. So now I wanted to share my PowerPoint because it has some pictures. Do you see my PowerPoint? No, right?
No, we don't.
Ah, nice. All right. So then, keyboard. No, not that. Zoom, help me. All right, share. Now I'm back over here. Share screen. Share my PowerPoint. All right, what do you see? The first slide or both?
Just one slide.
Looks like
Yeah,
just
just
slide.
one.
All right, so this is the periodic table of Fermi surfaces. So do you see my mouse?
Yes.
All right,
Yes.
so let me go back. There we go. All right, so here you see this is lithium all the way down to cesium. You can see it here. This is almost like a sphere, right? This is the lithium, this is the sodium, all the way to cesium. They're almost like sphere. If you look at them, they're almost like perfect spheres. But then this one already looks like something weird is happening at the surfaces right here, but they still look almost like spheres. If you look at gold, copper, and silver, they're also almost like spheres, but they're a little bit different because they have these little circles right here. But what happens then is that these are the alkali metals that give you one electron to conduct. And these are the noble metals that give you one electron to conduct two. Now, beryllium has this Fermi surface, so you see it's not a sphere. Some of them are really weird. This one right here is one of the, so the density of state of iron for the up electrons. And actually iron is a ferromagnet. So the ferromagnet means that there's actually a difference between being a spin up and spin down. So if you look at iron right here, this is the spin up and this is the spin down. So there's more electrons that are spin up versus electrons that are spin down. The Fermi surface is very different. Other ones that are interesting, for instance, cobalt right here also has that, and nickel. Nickel is very different between up and down electrons, and those are the ferromagnets.
Sorry, regarding iron, you said that there are more with spin up than spin down. Is that because the Fermi surface for the spin up is larger, so offers more location?
Yeah, because it's larger.
Okay.
And you're assuming that a spin up is the one that the magnetic field is applied, right? So it's a ferromagnet with the spin up. That's why that's how I define a spin up, the one that has more electrons.
Okay, thank you.
All right.
Why are some surface missing, like lanthanum one, or I don't know, silicon?
Because they're not metallic.
Oh, right. Makes sense.
All right. So yeah, semiconductors and insulators look different than this.
You can add something too.
Go ahead.
So the I was wondering. So fermions are electrons, right? And this Fermi surface is basically the distribution of fermions around some geometry.
Yeah.
Also, is this an actual geometry? And also, what is the relation between this and the fermions?
So
If there is.
the Fermi surface is a picture of all the electrons that it's a picture of all of the K values that have electrons at the Fermi energy. So if we were to look at these guys right here, right? All of those electrons, they look like spheres because all those electrons are the same. But if we compare it, for instance, to this one right here, or even one that looks like a little bit different, just a little bit different, like this one right here. This one is not symmetric. It's not a perfect circle, because that means that instead of being a sphere, the electrons that have the same energy sometimes have different direction of the wave vector. So let's see, can I draw here? I think I can. Let me figure that out.
But you said the direction or the spin up is determined by the number of electrons.
All right, so let me draw this in the whiteboard again. All right, so this is it's simpler to draw here, so let me do this. What we had before was a sphere like this that was kind of symmetric, right? So now some of them now look like this. Let's say it looked like that, like a weird formation, right? What that means is that there's an electron here that is traveling with this wave vector, because remember that this is still in kx and ky like that. So this direction has the same energy than this direction. Electrons traveling on that material are not going to travel at the same speed if they're going in this direction than if they're going in that direction. And that kind of asymmetry is what you see in that Fermi sphere. Well, not Fermi, in that Fermi surface, it's not a sphere anymore, right? So that means that there's an asymmetry on that system. Going from a sphere to something that now looks like this tells you that there's particular directions that are favored for more speed, even though these guys here, here, and here would be having the same energy on the system.
Can we think of this as the trajectory that the fermion makes?
Exactly. And that's exactly how you would map those out.
But also, I know that the speed of those is 1,000 trillions per cycle. How can they keep up if it's not circular? I always thought the trajectory should be circular so that they can keep up with that speed. So apparently they're not. They move with different speeds in different locations then, based on this.
Yes, they move
I
at
see.
different speeds in different locations based on this kind of system. In fact, there's directions that you're more likely to be moving, right? In materials, sometimes it's easier to go in this direction than that direction. And that's what these pictures are telling you.
Okay.
Any other questions regarding the Fermi surfaces?
So are these surfaces related to the way the orbitals of the atoms are shaped?
They're coming out of quantum mechanics, but not exactly like this is the way they are or anything like that, based on the orbitals. But they're more like quantum mechanics, which also tells you that they're coming from the orbitals.
Okay, thank you.
Next thing, let me redo this, my PowerPoint. And I hope you can see it there. You're seeing the Fermi distribution now, right? Or something else?
We see the other view, the presenter view, I think.
Oh,
Yeah, it's the Fermi distribution. Yeah.
all right. Well, even if you see the other one, right? You were seeing that was the Fermi surfaces. Now this is the Fermi distribution. So we had a function FOB there. This is the function FOB. And this is the Fermi distribution of the system. So because they're fermions, when the temperature is very low, and in this case, the temperature, so you have a Fermi level right here. The Fermi level is located here. And you see my mouse, right?
Yes.
All right. So the Fermi level is located here. So this is 1 up to the Fermi level, and then goes down to 0. And then you have that kVt would be the quantity that tells you the temperature. So if this was 0, kVt is the temperature goes to 0, kVt is 0, you will get the Heaviside function, the one that is the theta function. But when the temperature starts getting higher and higher, what you start seeing is that it rounds off at the edge and it rounds off at the bottom. And then if the temperature is higher, like in this case, 0.25 is kVt, you have this difference with it. If the temperature gets higher to 0.5, you get the green one. So that's the distribution of fermions. It's either 1 or 0. So now the classical distribution of a system from a StatMech is the Boltzmann distribution. And here I'm giving you the Boltzmann distribution for 0.5. And if you look at it, the Fermi distribution at high temperature, this green one, looks exactly the same as the Boltzmann distribution at high temperature. They are equal on this range, but they're not equal at low temperatures. Questions? So those are the Fermi distributions. And what happens then? We have to talk about what the Fermi distribution is. And at low temperature, it looks like the Heaviside function. At high temperature, it looks like the Boltzmann distribution. And then the next thing you have to know is, I'm talking about high temperature, right? So what do I mean by high temperature? What I mean by high temperature is that the temperature will be related to the Fermi energy divided by the Boltzmann factor Kb. And if we do that, although it's not really specified, but this is like a good guess, that means that high temperature means around 10,000 Kelvin or more. So when you have fermions at room temperature, it's almost like so close to the, way closer to this low temperature limit than to the high temperature limit. 10,000 Kelvin is inside the sun, right? On the surface of the sun, what is the temperature? So those are the two limits that we have. And that's how high the temperature would be for your particles to behave as classical, your electrons to behave as classical particles, around 10,000, 25,000, something like that. So that means that your system already melted, right? Because everything melts at those temperatures, unless they're at super high pressures, before they start behaving like classical electrons or classical particles. All right, so any other questions?
So they behave classical below 10,000, right? That's what
No,
you
they
said.
will behave classical around 10,000
Only around 10,000, I see.
or higher.
Otherwise, they will melt or they will freeze. They will not move.
We
basically.
have that this degenerate Fermi gas that is very close to the Heaviside function for most of the cases. So 300
Then if you,
is so close to 0 compared to 10,000. So your
if you don't, oh, sorry.
quantum particles,
Continue.
these electrons in normal situations are quantum particles. You have to go to the super high temperatures for them to not be quantum particles. That's what this Boltzmann distribution tells you.
Well, that means the normal atom that we have, like on my skin, is it now at high temperature?
No, low
And
temperature.
how we're not observing it? Oh, but they are moving. They behave like classical. Oh no, they don't behave like classical, right?
Yeah, they behave like quantum particles.
Oh, yeah, yeah.
But they're all moving in
Okay.
different directions, so they average out, right?
Mhm.
Yeah. All right. So that's where I wanted to stop for today. And just this discussion of occupation probability. So far, we have covered in the book up to page 27. But I think that you can follow the next few things because it's dimensional crossovers. And that basically tells you what happens when one of your dimensions, so we just talk about 3 dimensions, but what happens if one of your dimension gets tiny, right? Compared to the other 2, or 2 dimensions get tiny and the other one is big, things like that. So you should be able to follow the discussion there on dimensional crossovers for electronic structure. And that's, I think the Fermi distribution is in page 33. But that's, I think, good enough for us to stop there. And then I'll give you a homework assignment. I still need to write it like I told you guys, but you'll have it this weekend for sure. All right. So if you don't have any questions, I'll see you next week.
Thank you. Have a good weekend.
See you.
Thank you.
Thank you.